Let's now discuss the components of the RPC latency. By now, we are all familiar with the semantics of RPC, namely, in an RPC, the client is making a remote procedure call to a server, and it has to send the arguments of the call to the server so that the server can execute the server procedure and return the results back to the client. So if you look at the components of the RPC latency, it starts at the client with a client call. So the client call subsumes a number of things. Number one, it is setting up the arguments for the call. The client has to set up the arguments for the procedure call. And then it makes a call into the kernel. And once the kernel has been informed that it wants to make this call, the kernel validates the call and then marshals the arguments into a network packet and sets up the controller to actually do the network transmission. That entire set of activities that the client program and the kernel is involved in getting ready a network packet to send out is subsumed in this one line, which I say is the client call. The second part of the latency is the controller latency. And this is the part where the controller says, well, there is a message to be sent out. I know where it is in memory. I have to first DMA that message into my buffer and then put the message out on the wire. That's the controller latency. And so this part of it is in hardware. And as operating system designer, we're going to take what the hardware gives us. Controller latency is what you have, that given by the hardware. The third part of the latency is the time on the wire. Now this really depends, as one might imagine, on the distance between the client and the server. The limiting factor, of course, is speed of light. So depending on the bandwidth that's available between the source and the destination, perhaps if you have to go through intermediate routers and so on, it's going to take a certain amount of time to go from the client to the server machine. And that we call as the time on the wire. So then the message arrives over on the destination node, and it arrives in the form of an interrupt to the operating system. So the interrupt has to be handled by the operating system, and part of handling the interrupt is moving the bits that come in on the wire into the controller buffer, and from the controller buffer into the memory of the node. So all of that activity is subsumed in this item number 4, which I call as the interrupt handling. So once the interrupt handling is complete, then we can set up the server procedure to execute the original call. Now what is involved in that? Well, you have to locate the server procedure. And once you locate the server procedure, you have to dispatch the server procedure. And once you dispatch the server procedure, you have to unmarshal the network packet that comes in as the actual arguments for the call that the server procedure has to execute. So all of that setup is first done, and then the server procedure can actually execute the call. So this is the 5-step process from the time the client says, I want to make an RPC call, to the point of actually executing the call. These are the layers of software and, of course, hardware and time on the wire, by which time you're ready to execute the server procedure. So even though it looks like a simple procedure call from the client's point of view, there is all this latency to be incurred in executing a remote procedure call. So at the end of step 5, the server is all set to execute the procedure. Let's see what happens then. So step number 6 is server execution, meaning that it is actually executing the procedure. And of course, this is not under our control as operating system designer, because at this point, the amount of time that the server is going to execute this procedure depends really on the logic of the program that has been written as a client-server program. And then finally, once the server procedure is completed execution, then it says, okay, I'm ready to send the reply back to the client, and that's where we pick up again. So what happens is that at that point, you're receiving the results. So once again, just like when the client wanted to send the arguments, you had to convert the actual arguments into a network packet and send it out on the wire. Similarly, when the server is ready to reply, you have to take that reply, which is the results of the execution of this procedure, and make it into a network packet. And at this point, once it has been made into a network packet, it has to be handed over to the controller, and the controller does exactly what we did on this side, which is to say the controller latency is going to be incurred. So that's why you see item number 2 appearing all over again in the return path. Similar to sending the arguments over to the server on the wire, the results had to be sent on the wire back to the client. And so you see that item number 3, which is the time on the wire, is reappearing on the return path as well. Come over to this side. The incoming result message is going to result in an interrupt on the receiving node, the client node. And that is exactly similar to what happened on the server side, item number 4. So you see item number 4 reappearing on the return path as well. So that is the interrupt handling part. And once that interrupt is handled, the operating system on the client side says, oh, this was on behalf of this client. Let me redispatch the client, set up the client so that the client can then receive the results and restart execution where it left off. So the only 2 new things that we added in the return path was item number 6 and 7. 2, 3, and 4 was exactly the same as what we saw on the way over to the server, that is being repeated on the way back to the client. So that's the 7-step latency involved in the RPC, not worrying about the actual execution time of the server code itself, because that is not in the purview of the operating system. It is in the purview of the client server program that the app developer has done.